Okay, so yeah, we just talked about prodrugs and how this is an example of a prodrug design that improves the oral bioavailability of naltrexone, the opioid antagonist, one of the opioid antagonists. All right, so let's go into some of these reactions now. There's three kind of classes of metabolic machinery that causes phase 1 drug metabolism. All right. P450, which we've talked about a bunch, it's present in most tissues, but there's a lot of this in your liver, microsomes, types of cells that are found in your liver. P450 contains heme, which enables a lot of really cool reactivity that we don't even see in the laboratory. So it's kind of a very unique enzyme system, and it causes some kind of magical transformations that are very unique to our bodies. You can't just throw in a chemical to do a lot of these things. All right. There's different isoforms of P450. 3A4, 2D6, 2C9, 1A2, and when we think about why does this matter, when you think about like drug side effects and interactions, two different drugs you might take, one interacts with the other. Sometimes a drug will maybe activate or inactivate one of the different isoforms of these things, and that isoform may be involved in the metabolism of another drug molecule. So that can actually maybe cause a problem. So that's why this has to be studied very carefully in clinical drug development. But also remember that it's cool that you can do a lot of these studies in vitro, and you can actually purchase the different isoforms of P450 microsomes. So you can actually purchase microsomes for different species, and actually do a lot of these studies really just in test tubes, essentially. So P450 can catalyze oxidation and reduction chemistry. Generally speaking, oxidation is the more common one, I think, that we see. But here and there, reduction dominates also. Depends on the drug a little bit. And then we have a different enzyme class called these flavin-dependent monooxygenases, called FMO. What they do is a little different. They directly oxidize like a nitrogen or sulfur on the atom. Okay. Usually P450 oxidizes a carbon, like maybe a carbon next door to a nitrogen, or carbon next door to an oxygen or sulfur. So this can be a little different. All right. So that's why we call this direct oxidation. And then we also have other enzymes, esterases, amidases, peptidases, proteases, things like that, that are soluble. So they're just present in the plasma, and they catalyze hydrolysis reactions to cleave esters and amides and things like that. So that we'll see examples of that as well. This shows kind of a catalytic mechanism for how P450 works. Essentially, on the left here is the substrate coming in with like a CH, right? And then the oxidation will kind of at the end it'll spit out like an OH, right? Like an alcohol or something. P450 often does that in an oxidation manner. So how does it kind of work? I mean, the steps are pretty well characterized. Essentially, your substrate comes in and it kind of it's interacting with P450. P450 is natively in the iron 3 plus oxidation state. This gets reduced, iron 3 plus gets reduced to iron 2 plus with sort of a cascade involving P450 reductase. So it's a reducing enzyme. And it uses another iron cofactor that gets oxidized. So iron 2 and the cofactor gets oxidized to iron 3. And then and then that gets re-reduced back to iron 2 using FADH2, which is one of the biological reducing agents, right? And then in a cascade, the FAD plus, which is the like an oxidized form, it gets re-reduced using NADPH and NADH. So it's kind of this little cascade. You see this kind of stuff all the time in biochemistry. Anyway, so iron 3 got reduced to iron 2. Oxygen gets incorporated into the system, and there's a heme in P450 that interacts with oxygen. So iron is kind of bound to oxygen, O2. Then through a couple things happen with this NADP and NADPH and NADH, that essentially what happens is the oxygen is getting reduced, and also the iron is getting oxidized. So there's like a couple things happening. That's caused by NADPH and NADH. Okay, and then oxygen is basically lost from the system as water, leaving an oxygen which is ultimately going to be attached to the RH, and that eventually is how your molecule gets oxidized. So that's kind of a way to think about how the general catalytic system. So some of this is better understood than other parts of this. One paper, if you're interested in the mechanism of this, or if you're a biochemist, is J. Biochem Molecular Toxicology 2007, which talks about these steps in a little more detail. And there's other literature on this. Okay. All right. So let's go into some of these oxidative reactions now caused by P450. So what types of oxidation occur? Oxidation of an unactivated aliphatic carbon chain. I'm actually kind of the most fascinated by this, because unactivated means it just randomly installs an OH somewhere in the molecule at a position that's not totally logically activated, and it's kind of magic, right? We'll see examples of that. Then we have oxidation of activated CH groups. This is less surprising to me. So certain positions are kind of activated by a benzene ring or a alkene or something that sort of stabilizes the removal of a CH. Epoxidation, which we've seen before when we've talked about like some of the toxic substances and benzopyrene and benzene. This is one of the ways that things can get oxidized. Aromatic hydroxylation. So a benzene can just get an OH installed onto it. Then we'll get into some of these FMO catalyzed oxidations. So like nitrogen and sulfur can be directly oxidized. Yeah. So that's like a different class. Remember, these top ones are mostly carbons getting oxidized. This is like nitrogen and sulfur oxidized, and it's not through P450. It's through something called FMO. Okay, so aliphatic carbon chains, which again is one of these things that I'm kind of personally fascinated by. So there's something called omega oxidation, or like if you have a chain of carbons, it's like the terminal methyl group or something. And then there's omega -1 oxidation, which is one carbon from the end getting oxidized. And here's an example, anticonvulsant drug with like an ethyl group on it, and it gets hydroxylated at the very end by P450, and also the one carbon away. So omega and omega -1 oxidation. Why am I so fascinated by this? Most likely the CH3 and the CH2, it's like losing a hydrogen atom, right? And then it's being replaced with an oxygen atom. And those are like not stable radicals. So you actually would go through a radical intermediate, and the radical intermediate is not super stable, and it's kind of weird. It's going through a sort of a thermodynamic mountain to get to these products. And I'm kind of surprised because nature usually doesn't do that. But at the same time, nature and our bodies really don't like molecules in our circulation, so they do kind of cool things to ultimately excrete them. Okay? Another one, cyclic aliphatic oxidation. So what does that mean? So cyclic, maybe a ring. Aliphatic is also like just carbons and cyclohexanes and stuff like that at non-hindered positions. All right. So this is a vasodilator and kind of a simple molecule, pretty simple molecule, right? And P450 can just install hydroxy groups on these rings randomly, and that aids in excretion, or you can do phase 2 metabolism off the hydroxy group. So this is one of the cool things that another example of a cool thing P450 does. And these are these non-activated alkyl chains. Then we have the oxidation of activated CH groups. So by activated, I mean that the CH, if you remove the CH, the H atom, it makes a radical that might be a little more stable, and then maybe stabilized by resonance or something, and then it kind of makes sense that the oxidation occurs there. So there's two types: oxidation next to a pi bond. Oxidation next to a pi bond. This is totally makes sense that this is what happened, because it's pretty easy to oxidize next to a pi bond. Example: this is was it pentyl benzene? So a molecule with like a chain off of a benzene. It's pretty easy for P450 to just turn this position into an OH. And I'm not going to show it, but I mean, imagine if you have a radical there, right? If I have a radical at this position, I can draw resonance. I can do Fischer arrows to draw resonance to delocalize the radical all around the benzene, right? Just like I can do it for a negative charge or positive charge. There's all this like delocalization through resonance. Okay, and that's why that's activated, right? That's why we call it an activated position. Okay, and alkenes do this also. All right, so that position next to an alkene, if I take the H off, or P450 takes off the H atom, the hydrogen atom gets removed, you're left with a dot, a carbon, and that dot is also resonating with the alkene. So that explains why this position is activated as well to hydroxylation. Also alkynes. So you can imagine an alkyne, that position right there is activated so that if an H gets removed, even an alkyne can resonate the electron, the radical. Okay, that's what we mean by activation. And it's also if it's neighboring like a nitrogen or oxygen, there's some kind of resonance stabilization of that too. Okay. So we can oxidize next to a heteroatom like nitrogen and oxygen, and that's going to lead to things like dealkylation of a methyl group and things like that. So here's a general example. If I have X, so it could be oxygen, nitrogen, sulfur, and then I've got a couple carbons, P450 can oxidize this position here. And also, if I envision the radical, like there's a CH2 there, envision one of the H's come off and I get a radical. That radical is resonating with the X group, and there's a little bit of stabilization. That's also what I mean by activation. Activated CH groups. All right. So this position is easy to oxidize with P450 to the hydroxy group, and once that happens, the oxygen can swing down, kick off, break off, and now we've basically lost this alkyl chain. And that is a very common way that P450 basically destroys molecules or metabolizes them, and deactivates them is basically by cleaving off the alkyl bonds. Okay. That whole process has a name that metabolic chemists use, oxidative dealkylation, right? We're oxidizing. The first step is the oxidation, catalyzed by P450. And then the oxygen swings down, breaks off that thing, and we have a net dealkylation. We've lost the propyl group. The propyl group in this case ends up as like propylaldehyde, and that probably gets oxidized to like propionic acid to get excreted, because aldehydes are not very stable in our body or also just in general. Okay, so let's show a couple examples of this oxidative dealkylation. Oxidation of a CH adjacent to an amine, and this is very common. You know, a lot of drugs have amines, and they have a methylamine or a dimethylamine, and those methyls can fall off. So here we're just showing like propylamine just as a non-drug example. So P450 can oxidize next door to the nitrogen and give it a hydroxy group, and then basically just cleave off and make ammonia and propylaldehyde, or propanol, I guess it's called. But also if you have a secondary amine, because the primary amine up here, secondary amine, the same kind of thing can happen, where the carbon gets oxidized to a hydroxy group, and then the hydroxy group swings down, kicks off, and now you've basically just cleaved off this 3-carbon chain, right? This 3-carbon chain's gone now, and now you have a, that chain gone. You have another amine, like a primary amine, and this aldehyde, and the aldehyde is probably gets oxidized and lost as well. What about a tertiary amine? With a tertiary amine, it can get oxidized by P450 to make the little alcohol thing, and then that alcohol can swing down, kick off, and now you have a secondary amine. So the tertiary amine gets converted to a secondary amine. Net effect, oxidative dealkylation. We oxidatively removed the propyl group, right? Example of this is oxidative demethylation of diazepam, which is Valium, the sedative molecule. So you have a methyl group in Valium, and P450 will oxidize it to this intermediate with the hydroxy group, and then the oxygen kicks. What happens? The oxygen kicks in and breaks the bond off, and you make the amine, or I guess technically an amide here, and then that creates formaldehyde. Can you see how that happens? Envision a oxygen lone pair, right? A lone pair on oxygen, kick in and break the bond off, and that essentially creates formaldehyde, right? That's a very common fate of methyl groups and methyl groups in drugs, is they get oxidatively dealkylated to make formaldehyde. Okay. What's this called? I don't know if you know the name of this. This has a name. It's called if you had, I can't draw this easily for you guys right now. But if this was an oxygen, say it was an oxygen, and then this kind of halfway intermediate, it's called a hemiacetal. Hemiacetal. You may have heard that word in organic chemistry class. This is called a hemiaminal. It's like a hemi, H-E-M-I, aminal, A-M-I-N-A-L. So these intermediates are called hemiaminals, all of them. Hemiaminals. Okay. Anyway, if you like names for things. Okay, what about if we oxidize a CH adjacent to an ether? Well, that happens also. So phenacetin is one of the early NSAID analgesics, kind of like ibuprofen or Tylenol. I think the structure of this is vaguely similar to Tylenol, maybe with minus the ethoxy group or something. Well, anyway, yeah, so you got an ether here, and ethers can be oxidatively cleaved with P450. Same kind of thing. This P450 oxidizes the activated CH. Why is it activated? To envision the activation, imagine a radical. If you have a radical, you can actually draw a radical resonance with the oxygen. So there's a little bit of radical resonance. And like I just said, those nitrogen examples above were hemiaminals. This is called a hemiacetal. So a hemiacetal is the oxygen equivalent for that thing we were just showing. Anyway, so what happens? Now the oxygen kicks off, and you make an alcohol. This actually would create Tylenol. So this is sort of a prodrug for Tylenol. And acetaldehyde. And acetaldehyde gets excreted and removed through other processes. Oxidative dehalogenation of an aliphatic halide. Sounds scary. Dehalogenation kind of means loss of halogen, right? And an aliphatic halide maybe means a molecule with a halogen in it. So this is a metabolic process for molecules with halogens in them. So halothane is one of these volatile anesthetics, and they are actually, pretty safe and widely used. Can't use it extensively because it will cause liver damage. And how does it cause liver damage? Through its metabolism, right? Now, this CH right there, there's a CH right there. If that CH gets lost and you get a radical, there's extensive resonance stabilization with all the bromine and the chlorine, and not really the trifluoromethyl, but the bromine and the chlorine will extensively stabilize this position. So what's P450 going to do? It's going to oxidize that position. So mechanistically, probably through a radical, and then oxygen gets attached. And then you have this alcohol. And then the alcohol can kick in and kick off either the bromine or the chlorine. I'm showing you kick off the bromine, and that makes trifluoroacetyl chloride. And these are super electrophilic, and they can acylate your liver proteins and lead to hepatotoxicity. So this is an okay, short-term anesthetic, maybe for a short-term surgery, but it does actually have some liver toxicity. Is liver toxicity terrible? Well, your liver kind of regenerates itself. So if you have hepatitis, this would be a very bad drug. But for a healthy person, this could be used as a nice anesthetic for surgery without causing serious problems. And then water would actually also destroy the acid chloride and make trifluoroacetic acid, TFA, which also, that's highly acidic, but that's going to break down and lose its proton. All right. Another type of oxidation that's a little different, rather than just making an alcohol or something, is epoxidation of alkenes, right? So we know what epoxides are. Little 3-member rings with an oxygen in them. And those are electrophiles, which can be kind of scary because electrophiles might do damage to proteins or DNA as well. Example is diethylstilbestrol, which has an alkene in it, and it's one of these estrogen derivatives, kind of like tamoxifen, made first time in 1938. And anyway, P450 oxidizes the alkene. I think it does it stereoselectively, which is not surprising because P450 is a protein, and proteins are kind of picky about stereochemistry. So it makes epoxide, and then that probably gets hydrolyzed to the dialcohol and then maybe excreted. Another example is carbamazepine, which has an alkene in it, in a part of this weird heterocycle. That gets oxidized by P450 also. So Yeah, I mean, do these all lead to maybe toxic intermediates? Not necessarily. Sometimes they do, though. And we talked about what were the horribly carcinogenic molecules we talked about when we talked about toxicology? Benzopyrene and even benzene can make highly electrophilic intermediates that are super toxic. Another case of a super toxic one is this molecule called aflatoxin B. It's a fungal natural product, hepatocarcinogen. One of the most carcinogenic substances known. So very nasty stuff. It's because it's very readily oxidized and attacks DNA, or DNA attacks it. So P450 oxidizes the little dihydrofuran right here to make an epoxide, and DNA very efficiently attaches to that, and then this gets attached to your to DNA, and this kind of these kind of molecules that get attached to DNA will lead to mutations and mutagenesis and in some cases carcinogenicity. All right. What about aromatic hydroxylation? So benzenes can be hydroxylated, usually at the para position, if you have a para position, the least hindered position, P450 likes to do. And that's kind of like when we showed the cyclohexanes earlier, the least hindered positions were the most readily oxidized. So Miniprin is an antidepressant drug, and it has a benzene, and benzenes are pretty easily hydroxylated by P450. So, and then that can be further conjugated with stuff for phase 2 metabolism. Interestingly, electron poor rings are not oxidized. That means if like a benzene with a substituent on it, like a fluorine or a chlorine, may prevent oxidation. And it's used as a strategy to prevent aromatic ring metabolism. So if you have a drug where you have a benzene that's getting metabolized, sometimes people add a fluorine or a chlorine, and that'll kind of either block P450 or also just deactivate P450. So it just doesn't work. An example is probenecid. This, I forgot what this molecule is. It looks like maybe a sulfonamide, maybe an antibiotic. But it's extensively deactivated, right? You have a carboxylic acid and a sulfonamide, and those are both sucking electrons to the left and the right, and the benzene is just not very electron rich and likely to go react to the P450. Another one, chlorpromazine or thorazine. It's an antipsychotic drug. So it has a chlorine aromatic on the left and just a normal aromatic ring on the right. The right side aromatic ring does get oxidized. The left side doesn't, and that's probably due to the chlorine being electron poor and pulling electron density towards it. Okay, let's talk about these nitrogen and sulfur direct oxidations. So this was not using P450, but what's it using now? It's using FMO. All right, so if you think about amines again, a typical behavior is oxidation of the CH next door to the amine, and that makes an alcohol, or we call it a hemiaminal, as opposed to when it's an oxygen, it's a hemiacetal. And then this falls off. The oxygen kicks in, nitrogen gets kicked off, and you get aldehyde and an amine, right? So what's the idea of N or sulfur or direct oxidation? it would mean basically direct oxidation of the nitrogen to a higher oxidation state. So let's consider a couple of options for that. Oops. So one example is if you have a tertiary amine, it can get directly oxidized, and it uses a different enzyme called flavin monooxygenase, which has a cofactor associated with it, and essentially you get something called an N-oxide, which is a higher oxidation state of an amine. Usually something else happens after this, so this is like an intermediate for something else that's going to go on. You can also imagine amide, like this tertiary amide, where the nitrogen gets directly oxidized as well, and you would get a amide N-oxide. Now this can also happen for primary amines, so primary amine can be oxidized on the nitrogen to the N-oxide, or a secondary amine, and they get oxidized to also an oxide. Usually, though, these will definitely shuttle to something else, another functional group, maybe a nitrone, and we'll see some of those other weird nitrogen functional groups in a second. And then sulfur does it also. Sulfur has higher oxidation states, like sulfoxide, like DMSO, dimethyl sulfoxide, and furthermore, sulfoxides can be continued to oxidize to the sulfone. The sulfone is like a ketone, kind of, I guess. I don't know. Well, I guess a sulfoxide is closer to a ketone, but anyway, sulfone sounds like a ketone, roughly. And it's the two double bond oxygens, all right? Okay, so these reactions use these FMO enzymes, not commonly P450. There are a couple occasions where P450 is used to do a direct oxidation, and we'll actually see those at some point here. So the mechanism is that these, the FMO enzyme has this flavin heterocycle system, and it actually gets reduced initially with NADPH. So NADPH is a biological reducing agent, and so what happens is, pretty cool. It's almost like sodium borohydride or lithium aluminum hydride, right? It's a hydride donor. So the nitrogen kicks in, the double bonds shift over, H minus gets transferred onto the flavin, and that pushes electrons all the way over to the oxygen. And then that is activated to attack oxygen. So oxygen swings back all the way, and we basically attach diatomic oxygen to this carbon atom. So this thing's called a hydroperoxide, right? Hydroperoxide, and then this is the active form of the enzyme, and your amine or sulfur or whatever lone pair just goes and attacks, grabs the oxygen, breaks it off, and now you have it. So that's essentially the mechanism of these FMO enzymes. And then nitrogen swings back, kicks off the oxygen, basically to lose water, and you start the whole process again. So that's how FMO enzymes work. So a couple examples. Tertiary amines, right? Nitrogen with three things on it, and I think I misspoke earlier. Yeah, these usually will oxidize and stop. It just makes the N-oxide, and the N-oxide is actually relatively stable, so it's not like something else would happen. Guanethidine is a hypertensive drug, and it oxidizes on the amine. You get the N-oxide, and then that's actually a semi-stable species. It's not like it rearranges to another functional group. Another example, another antihistamine, cyproheptadine. I'm double checking that name. Paracetin, and it oxidizes also on the tertiary amine to the N oxide. Okay, so then the secondary and primary amines rearrange to other functional groups like nitrones. How does that work? So phenfluramine is a anti-appetite suppressant. It's in one of the amphetamines. Amphetamines are typically benzene, 2 carbons, and nitrogen. Often a third carbon where the nitrogen is. And this was withdrawn due to heart disease problems. But anyway, it's a well-characterized drug. It's got a secondary amine, and FMO will oxidize the nitrogen. And then what happens, then P450 will come in and oxidize the carbon. So it's like a double oxidation. First it oxidizes the nitrogen, then it oxidizes the carbon. Then the nitrogen swings in, kicks that off, and now you have something called a nitrone, which is a different functional group. It's kind of like a ketone almost, right? A ketone being just an oxygen there. But then it can kind of, or what are those other things? There's all those functional groups that are like C double bond N and then like a carbon, right? Remember that? C double bond N carbon. Kind of ignore the oxygen, right? What's that called? If you ignore the oxygen, what's that called? It's definitely a organic 2 functional group. It's called an imine, right? An imine is C double bond N and then carbons or whatever. And those are susceptible to chemistry like hydrolysis. So this thing kind of acts like an imine. It can be hydrolyzed, and that would give you actually the ketone, right? So there's some follow-up chemistry that can happen to a nitrone. Okay, primary amines can do this also, and they can. There's a lot of different things that can happen with primary amines. You'll often get a mixture of metabolites. Some of them are active, some of them are inactive, etc. Okay, so this is back to the amphetamine structure. So it's a benzene, 3 carbons, nitrogens on the second carbon, and this form of amphetamine is actually a commercially used or pharmaceutically used amphetamine, Adderall, which is a stimulant used for like ADHD and attention deficit disorder things, and so it is metabolized also using FMO, so direct oxidation, and this can then the base can actually take off the proton and kick off the OH, and that makes an imine, like I was saying, an unsubstituted imine, right? Now imines can be hydrolyzed, so water would just kind of attack and kick off ammonia, and that would make a ketone and hydroxylamine. Sorry, not hydroxylamine. That would be ammonia, NH3, if it got hydrolyzed off, yeah. Okay, and then, but furthermore, the imine can be direct oxidized again by FMO, and then makes an oxime, and oxime is another imine derivative, and that can be further. Okay, I think what I was trying to say in this figure was that, okay, if this hydrolyzes, you make the ketone, right? But the oxime can also hydrolyze, and that would actually make the ketone and hydroxylamine. So this is kind of right, it's drawn a little funny. So yes, if this hydrolyzes off, it would make hydroxylamine. But if this hydrolyzes off, it would make ammonia, NH3, right? Okay, but anyway, the oxime can further oxidize on the nitrogen with FMO and make this higher oxidation state species. And it can rearrange to make a nitro species. So there's basically 3 common metabolites of Adderall: the nitro, the oxime, and the ketone. Okay, N-benzylamphetamine, another secondary amine. Okay, so what are some of the things that can happen to a molecule like this? Well, P450 can oxidize the carbon, make the, what's that called again? not hemiacetal, but what? It's the hemiaminal. Okay, and then these all are always labile for cleavage, so the oxygen kicks down, nitrogen gets broken off, and you make a ketone and an amine. That's one of the pathways. P450 oxidation of the left carbon. P450 can also oxidize the right carbon, the other secondary amine, and then you would, now this hemiaminal would break down, kick off the nitrogen, and make a different amine, which is also, again, this is just plain old amphetamine, or what Adderall is. And then furthermore, FMO can do a direct oxidation of the secondary amine to make the N oxide, and then how did we get from this N oxide to the nitrone? So that was, we saw that with the fenfluramine metabolism a second ago. So basically what happens is P450 would oxidize the CH, right? And then nitrogen would kick that off, and then you'd get the nitrone. So yeah, there's a lot of metabolic pathways for these secondary amines and primary amines. Okay. Okay, so nicotine is another interesting drug. With it has a tertiary amine. It also has the pyridine, which is metabolized differently. I believe the pyridines can do a direct oxidation, but usually it would just stop there and make the N oxide. But anyway, the tertiary amine is kind of interesting because there's a lot of other stuff around. So what are some of the metabolic pathways for nicotine? One thing is P450 can oxidize the neighboring carbon next to the nitrogen, and that makes, what's that called again? Not hemiacetal, but hemiaminal. It's like animal, but the letters are rearranged. Aminal, hemiaminal. And that can actually undergo a second oxidation to the amide. So in this case, this is a kind of a cool alternate thing that will happen with P450 is it oxidizes a second time. And when it oxidizes a second time, that oxygen can kick off the first oxygen, and then you make an amide. And then it can oxidize again. P450 can oxidize on the other side. And then that is another hemiaminal, and that oxygen can swing in, kick off the nitrogen, and then you make this kind of ring open metabolite. So all of these things that are observed, this isn't just theoretical. These are all pathways, and part of what a pharmacokineticist would do, which kind of specializes in pharmacokinetics and like metabolism, is actually figure out what metabolites are formed and then propose these sort of pathways. So that's kind of a cool thing. When you have like mass spec and LCMS, it's I wouldn't say it's easy, but it's definitely a doable thing. Okay, so what about P450 oxidation of the N-methyl group? That makes another hemiaminal that can basically do a plain old dealkylation, right? We started by talking about this. It's called oxidative dealkylation. So making a hemiaminal, have it fall apart, and then you just loss of a methyl. That's called nornicotine. The name of that molecule is nornicotine. I think it's an active metabolite also. And then there's also the simple N-oxide formation of nicotine, which is nicotine N-oxide. Okay, what about aromatic amines, which are also called anilines, right? Aromatic amines are called anilines. Can we do a direct oxidation of them? The answer is yes. So one interesting thing is this is actually not done by FMO. This is done by cytochrome P450. Unusual because most of the N oxidations and S oxidations are all done by FMO. But anyway, that makes a hydroxylamine, so the direct oxidation of the nitrogen. And then phase 2 metabolism usually would occur to attach an acetate group. We'll talk about phase 2 metabolism in a second. It's I think it's S adenosine. No, it's acetyl with a cofactor. I just forgot what the cofactor is. So basically acetyl with a leaving group, and then nitrogen or oxygen kicks off the leaving group and makes the acetyl. Well, anyway, DNA can then attack, and sort of like it's a conjugated addition. DNA can attack the benzene, kicking the electrons onto the nitrogen, kick off the acetate, and now DNA is attached to your molecule, releasing acetic acid. And then this could lead to mutagenesis and potentially cancer, depending on the drug and the nature of the amine, or just plain old liver damage, which when it adds up can be a serious problem. A little bit of liver damage is okay. Okay, so for that reason, we consider anilines as it's called a toxicophore, which is like kind of like a chromophore, but for toxicity. But there are anilines that exist in non-toxic drugs. It's just and for example, Tylenol. Tylenol has an aniline. Generally speaking, though, a simple aniline with nothing on it, or like an NH2, those are usually associated with some kind of toxicity through something like this. So let's show the metabolism of acetaminophen or Tylenol. All right, so what happens is this is Tylenol. It's got a aniline with an amide on it. It's got an OH. So the speculated metabolism is P450 does a direct oxidation of the nitrogen, not FMO. So it's kind of another case where aromatic amine type things are metabolized by P450. And then a base takes the proton off, oxygen kicks in, double bonds, shuttle around to essentially kick off that OH. And then we have this kind of electrophilic quinone type derivative that can be attacked by certain things. And ideally what's going to happen is glutathione, which is our scavenger for biological electrophiles, is going to attack the carbon, kick the electrons in and onto the nitrogen, and basically re-aromatize the ring. And then we have glutathione, right? It's a small peptide type thing, and that is able to be excreted. So this is a nice kind of healthy way to metabolize and excrete Tylenol. But then the other problem is when DNA, or we'll say liver proteins and cytochrome nucleophiles and cytochrome P450 do this kind of attack and have this molecule attached to your biological nucleophiles. Then that leads to liver toxicity. And this is kind of the mechanism for why Tylenol is liver toxic, right? In small concentrations, small doses, it's not that bad, but if you take large amounts of Tylenol, it can actually destroy your liver and it can be fatal, right? Tylenol is a drug that's frequently used by people overdosing, intentionally or accidentally. Okay, so sulfurs can also be directly oxidized, and interestingly, so you have two pathways, and we can do an oxidative dealkylation with P450, just like we did oxidative dealkylation of amines. So P450 could oxidize the carbon and make this not a hemiacetal, not a hemiaminal, but a hemithioacetal. It's a sulfur version of an acetal, but it's the hemi version because it's It's got an OH. It's not what's a normal acid, a thioacetal? A thioacetal would be if you have like a carbon with two sulfurs on it. That's called a thioacetal. Anyway, this is a hemithioacetal. And then just plain old dealkylation. The oxygen kicks off the sulfur. You get a thiol out and formaldehyde. But it can also do direct oxidation with FMO, just like the other, nitrogen was doing. So this is one of those compounds that kind of looks like thorazine or chlorpromazine. So it says, and a lot of these are antipsychotic drugs. 6-member ring, a benzene with another 6-member ring with a sulfur, and then another benzene. And anyway, it's got a nice sulfide there, and this can be directly oxidized with FMO to the sulfoxide. Okay. Now, I mean, of course, when I looked at the previous ones with nitrogen, I just had a single nitrogen single bond to oxygen, and like nitrogen plus O minus. Let's go look at that real quick again. Let's go back a couple. Where's an example? Trying to look at like these things. So it's an N plus O minus, right? N oxide. So sulfur is doing that. Right? So it actually makes S plus O minus. But with sulfur, the O minus can kick down and basically form this, sulfoxide as drawn here. Nitrogen can't do that. And these sulfoxides have two resonance forms. Is it this one and also the one with the S plus O minus. All right. So yeah, we oxidize two sulfurs with FMO to the sulfoxides, and probably the nitrogen's doing that too. We're just not showing that here to the disulfoxide. And it's there's other cases where a sulfoxide can keep going. In this case, this is a known reaction, and I wasn't sure if it was FMO doing it. Probably FMO. Potentially could be P450. But this is an immunosuppressant and going from the sulfoxide to the sulfone. All right. What about thiocarbonyl? What is a thiocarbonyl? It's C double bond S. It's a different functional group. It can be oxidized as well. Sulfur is just notoriously easy to oxidize. So thiopental is a sedative. It's kind of in the barbiturate class of compounds. Barbiturates all kind of look like this, a 6-member ring, some double bond O's. Pentobarbital is a classic barbiturate also. Okay, so anyway, it's got a thiocarbonyl in it as a C double bond S, and that can be directly oxidized with FMO to the thiocarbonyl. It's called a thiocarbonyl S oxide, right? The thiocarbonyl S oxide. And these are very easy to hydrolyze or kick off because this is kind of now a good leaving group. And so water can easily sneak in there, push the electrons onto the sulfur, do a little more electron pushing, and then this gets lost as some kind of S oxide type thing. And then you're left with the C double bond O. And that is an active metabolite as well. This is a very common barbiturate used in surgery and as a sedative. All right, moving on. Moving on to reduction. We did oxidation. Now, what are some reductive methods for phase 1 metabolism? So it's relatively prevalent, important. I think what I was trying to say is not as prevalent actually as oxidation. I think my text got jumbled here, and usually oxidation kind of dominates, and so there's kind of a couple ways. A couple of things that are commonly seen. Ketone cannot be reduced to alcohol with cytochrome P450 and NADPH as a cofactor. How do you do this in the laboratory? Like if you're doing a reduction of a ketone in the laboratory, you use a hydride source like NaBH4, right? Sodium borohydride to do this. But with biological systems, they need a reducing cofactor like NADPH. Also, a common one is nitro to amine. Also using a biological reducing cofactor. Okay, so let's show some examples. Oh yeah, the interesting thing also is it can produce a new chiral center if the molecule's chiral. And then the question is, what is the chirality of the new chiral center? So this is another opioid antagonist, Naltrexone. I think we've talked about it a couple times now. But it's got a ketone, and what happens when P450 and NADPH react with this? It reduces the ketone, and this is kind of cool that the chirality or the stereochemistry of the new alcohol can form either way, and it is species dependent. So that just shows, so in chickens the hydroxy group goes one way, and in rabbits and humans it goes the other way, and it just shows that we have little species differences in our P450 enzymes that slight chirality differences in the enzymes that could lead the hydride to be delivered. In this case, the hydride is delivered to the front of the ketone, and in this case, the hydride, the H minus, is delivered to the back of the ketone, which is kind of weird. And then further phase 2 metabolism would occur, attaching stuff to the hydroxy groups, etc. So the stereoselectivity is species dependent. Aromatic nitro compounds are a common thing that can be reduced as well. Alright, and so a molecule like clonazepam, it's an anticonvulsant drug. It has a nitro group that is reduced, and it makes an aniline. And then anilines and amines in general are very easy to do phase 2 metabolism. Of course, this could it could potentially reoxidize, but that would kind of put you where you started. Most likely, the aniline is just quickly conjugated with something like glucuronic acid, and then expelled or excreted. Azo linkage. What's an azo linkage? It's RN double bond N R. It's kind of a weird thing, and they are actually found in some drugs, and it's something that can be reduced. What do you think it's reduced to? Basically it can cleave the double bond N, and you're left with R, NH2, NH2R, two different things. Cool example of this is sulfasalazine. It's a colon ulcer and rheumatoid arthritis drug, and it actually has almost like two drugs built into it, like a left drug and a right drug, and it's delivered orally, and then P450 breaks it down into the left piece and the right piece, so there's an arthritis drug. These are both anti-inflammatory drugs, and they basically you're delivering two drugs in a single molecule, which is cool, and they are both active metabolites and kind of NSAID activity, cyclooxygenase. This is not exactly aspirin, because aspirin has an acetate group on it, but it's in the same general structural class as aspirin, 5-ASA, aminosalicylic acid. So this is an example of a prodrug. You might also call it a codrug because it actually has two molecules built into it, which is cool. Hydrolytic metabolism. So this is not using P450, nor is it using FMO. This is just using enzymes like esterases, amidases, or proteases and peptidases that cleave esters and amides. And they're soluble enzymes. And these are found all over your body: the plasma, liver, kidneys, intestines. So it's kind of like very ubiquitous enzymes. Not carried out by P450 or FMO. So aspirin is actually readily cleaved. It's got an ester. Esters are easy to cleave. Now, interestingly, aspirin is also one of the, what do we call those things that will covalent, when an enzyme will covalently attach to a drug, is called a suicide substrate. So aspirin is a suicide substrate for cyclooxygenase, which is its drug target. And so in addition to it being broken down, aspirin is an acetate donor. So it can actually donate its acetate to cyclooxygenase, and that helps in the deactivation of cyclooxygenase. Cocaine has two esters. It's got a methyl ester and also this benzoyl ester. Both of these can be cleaved. We're showing the cleavage of the methyl ester up top using esterases. Malathion is an insecticide, so not something we would really consume orally, but it is it has an ester that's cleaved, possibly within the insect metabolism, and it actually, what is it trying to show here? Oh yeah, it has two esters actually. I'm sorry, two ethyl esters, and one gets cleaved and then the other gets cleaved. And these can also be studied, with liver microsomes, kind of like in vitro metabolism. Yeah, cool. So another example of esters being cleaved. Just like in normal organic chemistry, esters are easier to cleave than amides, right? Because esters are more electrophilic, amides are less electrophilic, so less likely to be attacked. And that's actually beneficial to us because all of our enzymes are based on amide linkages, right? Peptides. So amides being kind of stable is beneficial to us because otherwise our proteins would just kind of fall apart readily. So a molecule like procaine, also called Novocaine, which is used as a local anesthetic in like dental surgery, things like that, has a nice ester, rapidly hydrolyzed. But procainamide, which is an antiarrhythmic drug, looks very similar, and it's pretty crazy that it has deviant biological activity. But it's got an amide, and that's very slowly metabolized because it's an amide, right? And in this anesthetic propanidid, it has an ester and an amide, and the ester is cleaved preferentially, which makes sense because esters are more reactive, so the ester is more readily hydrolyzed. Amide is preserved. Otherwise, the sides of this molecule aren't that different, I guess. This is a little more sterically hindered, but it's really the nitrogen electronics that make it more stable. Okay, we're going to jump into phase 2 transformations next. I think I'm going to just do that in the next lecture period, the synchronous lecture. All right, I think we're done.